Good morning everybody, this is Shiva Biram signing in, and in this session I am going to explain you coil span factor or pitch factor and distribution factor regarding the armature windings of an alternator. Before going further, let me explain you what is meant by a pole pitch and coil span, so which are very much essential to understand this. Pole pitch is nothing but the distance between two poles, that is one north pole and consecutive south pole, and generally it is measured in number of slots. For example, if you have got 24 slots for a 4-pole machine, the number of slots per pole will be 24 divided by 4, that equal to 6. So here 6 is the pole pitch in terms of number of slots. Coil span means the distance between one coil side and another coil side of a particular coil. If the coil span is exactly equal to one pole pitch, then we say that full pitched winding. That winding is considered as full pitched winding. And if the coil span is less than the pole pitch, so less than in the sense the second coil side is not exactly one pole pitch away, rather than it is going to be placed short by one slot or two slots from the full pitch, then we say that that winding as short pitch winding, which results in this coil span factor or pitch factor. This particular thing is being considered because of certain advantages, and also saving of copper will be there as the length of the winding is going to be decreased. Here the coil span factor is going to be result because of that, and it is defined as, so here pole pitch is 180 degrees electrical, so which is known as the distance between one north pole and the consecutive or the next south pole. As we know that the coil span is the distance between the two coil sides, so which is exactly one pole pitch. If the coil span is exactly one pole pitch, then we say that that winding as full pitch winding. And if it is coil span is less than one pole pitch, means if you place the other coil side short by certain number of slots, then we consider that winding as short pitch winding or fractional pitched winding. Because of this, we get this coil span factor or pitch factor, which is defined as the vector sum of the ratio. It is the ratio between the vector sum of the induced EMFs due to short pitch winding to the arithmetic sum of the induced EMFs. So which is represented by Kp or Kc, which is equal to the arithmetic sum, the vector sum. Generally the vector sum will be less than the arithmetic sum, because arithmetic sum is nothing but the direct addition of two quantities. So this factor will be less than 1, obviously. So vector sum divided by arithmetic sum. If you consider ES is the so now let us consider that the winding falls short by one number of slot. So whatever one slot angle is there, that is considered as the short angle. So here this is represented by alpha. Alpha is the short pole angle or short pitch angle. Let ES be the EMF induced per one coil side, then the arithmetic sum is going to be equal to ES plus ES. ES is the EMF induced per one coil side, so two coil sides means the resultant arithmetic EMF will be ES plus ES, which is equal to 2 ES. And when you consider the vector sum, here the EMF induced in coil side is going to be have a phase difference of alpha degrees electrical from the previous one, because the second coil side is not exactly 180 degrees electrical angle. So here this is going to fall short by an angle of alpha. So now the vector addition can be given by parallelogram law of vectors. So consider the parallelogram of these two vectors, and this vector is going to give you the resultant, which is represented by ER, and using the formula we are going to have ER will be equal to square root of, so if PQ are two vectors making an angle alpha, the resultant will be P square plus root of P square plus Q square plus 2PQ cos theta. Similarly here ES square plus ES square plus 2ES square, the angle is cos alpha. So and if you simplify this, we are going to have 2ES square into, if you take out common from these two, 2ES square, we get 2ES square 1 plus cos alpha, and we know 1 plus cos alpha will be 2 cos square alpha by 2, resulting in 4ES square cos alpha by 2. The square root of this is equal to 2ES cos alpha by 2, and this will be equal to our vector sum, right? So we have got both the arithmetic sum is 2ES and the vector sum is going to be 2ES cos alpha by 2 divided by and 2ES. So these two are going to cancel each other and resulting in cos alpha by 2. So this is how we are going to have the formula for finding out pitch factor or coil span factor, that is Kp or Kc. Next, let us see distribution factor or phase spread factor. Let me give some introduction about this particular thing. Generally, when the three-phase winding is considered, the winding for one phase is going to have distribution over the number of slots allotted to that particular phase. Say for example, if M is the number of slots per pole per phase, corresponding to one phase winding, that can be either R phase, Y phase or B phase, corresponding to each phase, the winding is going to be distributed over the number of slot allotted to that particular phase, rather than concentrating in that particular slot. Of course, if the winding is placed in one slot corresponding to a particular phase, that is known as concentrated winding, and instead of that, if you distribute it, so the distribution winding is going to have a lot of advantages compared to the concentric winding. So that is the reason why the distribution winding is going to be considered for armatures, which results in, of course, obviously each slot is going to, the winding which is placed in each slot is going to have certain phase difference from with respect to the previous one. Obviously the resultant EMF is going to be decreased compared to the concentric winding. So because of that, this distribution factor or phase spread factor is going to result. Now let us go to the details. So when the winding is considered for one phase out of three, and corresponding to each phase, if the winding is placed in one slot, we call that concentric winding, that winding concentric winding. So I hope that I am clear to you. So whatever winding is there, that is placed in only one slot, but generally that is not being considered. The winding is going to be distributed over the number of slot allotted to that particular phase. So that winding is known as distributed winding. And here the number of slots per pole per phase again. So generally this particular parameter is going to be represented by the letter M. Slots per pole per phase is going to be represented by the letter M. So this helps us in the derivation of the formula for this factor. And let us consider beta as another parameter here, that slot angle. So slot angle means total is 180 degrees and n is number of slots per pole. So 180 degrees is the distance between north pole and south pole, and n is the number of slots per pole. So that gives you each slot angle, how much angle is there for each slot. And now the distribution factor is going to be defined as the vector sum of that particular EMFs divided by the arithmetic sum. Obviously this also will be less than the direct arithmetic sum, because arithmetic sum is the direct addition of the quantities. So vector sum results due to the distributed winding, and the arithmetic sum is due to the concentric winding. Now let us derive the formula for this. In order to derive the formula for phase spread factor, I consider here 3 induced EMFs as shown here. So this is the first one, this is the second one, and this is the third one. And each are going to differ by an angle of beta, because beta is the slot angle. So each coil side is going to be placed one slot angle difference with respect to the previous coil. Hence the vectors are going to have a phase difference of beta with respect to the previous one. Something like, AB is going to have a phase difference of beta with respect to OA, and similarly BC is going to have a phase difference of beta with respect to AB. And what I do is, in order to derive the formula, I extend the perpendicular bisectors from the 3 EMFs. This means joining all the middle points at drawing lines from the middle points at right angles, and these are going to meet at a point. So let us consider that point as P. So here these vectors are of equal length, and this angle will be exactly 90 degrees. So that is the same with all the other quantities. I am joining the other two ends of each vector. So here if this angle is beta, this angle will be equal to 180 minus beta, because the total angle will be 180 degrees. So again this small angle will be exactly half. Let me be more clear. If this angle is beta, this will be equal to 180 minus beta, because this total angle will be 180 degrees, and here this will be exactly 1/2. So 180 minus beta is the total angle. This will be divided by 2, which gives you the value of 90 minus beta by 2. So this angle will be 90 minus beta by 2. So this is a perpendicular right angle here, 90 degrees. So obviously this will be equal to beta by 2, because the sum of angles in a triangle is equal to 180 degrees. So 180 minus sum of these two angles, 90 plus 90 minus beta by 2, which results in beta by 2. So this angle will be equal to beta by 2. Obviously these two are of same value, so the total angle will be beta here. I am giving some points D, E and F. So in this triangle ODP, if you consider the triangle ODP, first of all, OA is the length of the vector, which is equal to 2, exactly half. OD will be half of this length OA, so OA will be equal to 2 into OD. And as we know, the arithmetic sum will be equal to OA plus AB plus EC, because all will be the same, which will be m times the value of OA. This will be the arithmetic value, arithmetic sum. Now if you consider the right angle triangle ODB and consider the sine beta by 2, so here this is beta by 2, sine beta by 2 is equal to opposite side by hypotenuse, OD by OP, and from this we get OD is equal to OP sine beta by 2, and we know the arithmetic sum is equal to m into OA, that is 2 OD. So substituting all these values, we are going to have the arithmetic sum as equal to m into OA is 2 OD. 2 into OD is nothing but OP sine beta by 2. OP sine of beta by 2. Right? So that's about the arithmetic sum that we have derived here. And next let us go for the derivation of arithmetic sum here. So arithmetic sum will be from O to C. So if you join all the vectors, the resultant is going to be given by the length OC here. So OC is going to give you the vector sum of the all these vectors. And to find out this value, I am representing the middle point of this OC by Q. So OC is equal to now equal to 2 into OQ. Here this entire angle will be equal to m into beta, because this small angle is beta, and like that totally we are going to have m number of betas, so that this phase spread angle will be equal to m into beta. Half of this will be equal to m into beta by 2. And now this OQP is a right angle triangle. And from this OQP right angle triangle, find out the sine of this angle, that is m beta by 2. So we get sine of m beta by 2 is equal to opposite side by hypotenuse OQ by OP. So which gives rise to OQ, and from this we get OQ is equal to OP sine of m beta by 2. And we know that here the vector sum is going to be now equal to OC is equal to 2 into OQ. So the vector sum is equal to two into OQ, that is OP sine m beta by 2. So we have got the both things, arithmetic sum and also at the same time vector sum. So vector sum is 2 OP sine m beta by 2. So I am writing down here 2 OP sine of m beta by 2 divided by the arithmetic sum. Arithmetic sum already we have derived that, this one, m into 2 into OP sine beta by 2. m 2m sine OP sine beta by 2. So here OP gets cancelled and 2 gets cancelled each other, and we left over with sine m beta by 2 by sine beta by 2. Sorry, m sine beta by 2. This will be the formula for finding out phase spread factor or distribution factor. Now let us have another topic in this particular session, that is armature reactance, reactance. Generally, when you consider alternator, we are going to have the voltage drop due to three causes. One is the voltage drop due to the resistance. So all these things will result whenever the alternator is loaded. So voltage drop due to the resistance of the winding, and the second one is voltage drop due to the armature leakage reactance, because part of the armature flux is going to link with only that winding, which results in the leakage reactance due to the self-inductance of that particular winding. And in addition to these two, we are going to have another part of the reactance, that is resulting due to this armature reaction. So as we know well, whenever the armature carries current, because of that armature current there will be some armature flux which is going to be established. So the effect of this armature flux on the main flux is considered as armature reaction, and this armature reaction depends upon the type of load that we are going to use. And put together, all these things are known as synchronous impedance, that is resistance plus the combined effect of XL leakage reactance and armature reactance, and this combined Z is known as synchronous impedance. Let us see how this armature flux is going to show its impact on the main flux as the load varies. So when you consider the resistive load, R load, so let me draw the vector diagram in order to have the explanation. So this is the main flux which is established in the space, represented by the phi m, and as you know that the EMF induced will be always 90 degrees lagging with respect to the main flux because according to Faraday's laws of electromagnetic induction, d by dt of the flux. So obviously if flux is sin theta, obviously the EMF induced will be cos theta, which is going to have a phase lag of 90 degrees. So this is universal. Always the EMF induced is going to lag behind the corresponding phase flux by 90 degrees. And as it is resistive load, the current will be in phase with the voltage. So in the armature winding, the armature current will be in phase with the so as the armature current is in phase with the voltage, in the same direction the flux of the armature will be there. So phi A will be in the same direction. So as a result, you can observe that this is the effect of armature flux is disturbing uh, the main flux, so distorting. You can say this effect as cross magnetizing. So that is you can say that for R load the effect of armature reaction will be cross magnetization. And when you consider the inductive load, for inductive load, so consider the main flux and the induced EMF will be 90 degrees lagging behind. And now for inductive load, the current is going to be lag further by 90 degrees with respect to the voltage. So the armature current will be now exactly in this direction. So the armature flux will be in the same direction. Here you can see that this armature flux is going to exactly in opposite direction to the main flux. So here this is both are acting in the opposite direction, the effect will be demagnetization. So for a pure inductive load, if you consider, the effect of armature reaction will be demagnetization, means the strength of magnetism is going to decrease in the space. Now if you consider for a capacitive load, so this is the direction of main flux that we have considered earlier also, and this will be the induced EMF EA lagging behind by 90 degrees. And now as the load is capacitive in nature, the armature current is going to lead the voltage by 90 degrees and hence the flux. So here these two fluxes are going to act in the same direction, or you can say cumulative, so which results more value of flux in the space. So this results in magnetization. Hence for capacitive load, the terminal voltage will be a little bit more than the induced EMF because of this increased values of magnetization. So that's all for today's session. In the next session, I'm going to explain much more things regarding the alternator. So watch my videos, subscribe to my channel, and give your valuable feedback. Thank you very much. This is Shiva Biram signing off.